So the first parametric test that I'm going to go over is the Z-test. I'm actually just going to go over this as a demonstration of how the tests work. You're never actually likely to carry out a Z-test unless you want to do one by calculator, because most software doesn't do them. So I'm going to understand where parametric tests come from. Now, a criteria for using a Z-test is you have to have one treatment variable. You have to have treated and untreated, so you're applying one kind of treatment, so it could be one drug or it could be just gender. You need just one variable that's dividing your set of data into two different groups, two samples. It could be matched or unmatched data. Let's not worry about that particularly at the minute, but the thing that's critical here is large samples. You need at least 30 in your data set, and you have to have equal variances, which means you should have performed an F-test, but let's also ignore that for now. Now, the assumption is if the two samples are from the same population, you'd expect the difference between the means to be close to zero. So what you do is you find the difference in means between the two samples in terms of the number of standard errors between the means, as a ratio of the number of standard errors. This is a lot like coefficient of variation. So if I had a single sample, this is an exceptionally unusual one, but it's easy to work through the maths and idea for this. This means I'm comparing a single sample to an expected value that I found in the literature or from some control population. So the null hypothesis is there's no difference between the means. The alternative is there is a difference between the means. So I calculate the Z-test statistic from this formula. The mean of my sample minus the mean that I found out from the literature divided by the standard deviation, standard error of the mean. So that's now the problem is, do you need to estimate the standard error of the mean? That can be tricky, so you usually use it as the standard deviation of the sample divided by the square root of the sample size. Now, more useful and more common is the test for two different samples. So there is no difference between the means, or there is a difference between the means. Now we have to calculate a standard error, and this time we've got two standard deviations. We've got two variances. So the standard error of the difference between the two means is the square root of the variance of the first sample divided by the number in the first sample plus the variance of the second sample divided by the number in the second sample. Remember, variance is standard deviation squared. So that gives you the standard errors that you're going to use. Then to calculate the Z statistic, you subtract the mean of one of the samples from the mean of the other and then divide by the standard errors. What you're looking for is the difference between the two means to be large in terms of the number of standard errors. Now for a Z-test, it's a two-tailed test, so it's the difference between means can be either direction. So x1 could be, the mean of x1 could be bigger than the mean of x2, or it could be smaller than x2. So the critical value for a 95% confidence in your test, or a p-value of 0.05, is 1.96 standard errors. So if Z calculated is greater than 1.96 or less than minus 1.96, then you have a significant difference in the means between the two samples. You can calculate a p-value for the actual value of Z calculated, but it's somewhat tricky unless you have a calculator or unless you have a calculator or software. It's done instantaneously with most programs. So here is a single dataset example. A neuroscientist wants to test the effect of a drug on response time in rats. Got 100 rats, injects them with the drug. The mean response time taken from the literature is 1.2 seconds. The test is to see if the mean response time is not 1.2 seconds. So h0 mu equals 1.2, h1 mu does not equal 1.2. The test statistic is Z equals the mean of your sample minus 1.2 divided by the standard error of the mean. N equals 100. The sample mean for the rats is 1.05 and the standard deviation of the sample is 0.5. So therefore, let's fill in the numbers into the formula. You get 1.05 minus 1.2 divided by 0.5, which was the standard deviation, divided by 10, which is the square root of 100. That turns out to be minus 3. that is significantly lower than minus 1.96. So this is telling you that there is a significant difference in the response time of the rats between between control rats and these actual rats in the experiment. So it's actually significant even at a p-value of below 0.01. Now, to be honest, this is not a great design of experiment, because depending on what drug you gave the rats, you would know which direction the hypothesis should go. If you were giving them a stimulant, then they should have faster reaction times. If you were giving them a depressant, it should be slower. That would mean you could actually do a single-tailed test rather than a two-tailed test. But anyway, that's for experimental design. 2 independent samples example. So here we have a therapeutic program for Alzheimer's patients. So some are taught using visuals, some are taught using visual and verbal methods, and what you're doing as your outcome variable is measuring the number of words that they can remember. So group 1 has a mean of 5.43 and a variance of 11.702, and there's 30 in the group. Group 2 has a mean of 5.53 and a variance of 4.275, and n equals 30. Now already here you can see the variation is quite large compared to the differences between the two means. So this gives you a hint that it's not likely to turn out to be significant, but let's do the test anyway. Null hypothesis is there's no difference between the two means. Alternative is there is a difference between the two means. The formula for Z calculated is mean of the first one minus mean of the second divided by the standard error of the differences. So the first thing we need to do is work out the standard error of the differences. In this case it's 11.702 over 30 plus 4.275 over 30 and then square rooted. This turns out to be 0.7298. So I can put this into the Z calculated formula, and I got 5.433 minus 5.533 divided by that standard error of the difference, which equals minus 0.1 divided by 0.7298, which equals minus 0.137. That is nowhere near the minus 1.96 that you need for the critical value for a p-value of 0.05. So therefore I cannot reject the null hypothesis, and there's not enough evidence based on this sample. If I was to collect a much larger sample, then as the sample size goes up, then the standard error of the difference, because you're dividing by that sample size at the bottom, it will go down. That would mean eventually I can detect even very small differences between groups if my sample size is big enough. But does that make sense? In this case, the average number of words between the two different treatments is so small that it doesn't really make a practical effect. And can you justify ethically creating such a large experiment for such a small difference between the two? Now, there's one other thing that can happen, a sort of exception to prove the rule. It's just an interesting aside that you can do. So if your data set happens to be not normally distributed, but you've got a very large data set and it's continuous data, then you can use a Z-test about medians rather than means, and this will work. But as I said, this means having to do the Z-test by hand using those particular formulae. It's not something that's implemented in software, but if you desperately needed to do it, you could do it.